Let's get started. As always, anyone's allowed to ask any questions at any time. I will stop what I'm doing and answer. When we left off last week, I was working on a tracing profiler. In concept, it's pretty simple. We sample the instruction pointer of the CPU, every instruction, and count however many times it visits each address. So when we start the operating system in the emulator and run, we see all these numbers come back. Over the virtual serial port, it sends the results of the sampling, code segment, instruction pointer value, and the number of times it's visited. It does this for every single instruction, and it uses the serial port. So this is very slow. In practice, you turn it on for short bursts, usually. And that's how I envision it working. You don't leave it on for a very long time. You notice some code is running slowly. Narrow it down to a relatively small range of instructions. Turn the profiler on for that range, run it, and then look at your results. So where we left off, we were getting the results back from the serial port. We were able to look at them and correlate them to some degree with the names of the functions that we're using. So we have some code that generates a report. Actually, I'll do one. Let's see. Yeah, so this new command profile lets us specify symbol files. Oh, where's this one going to be? There we go. Specify symbol files and one of these log files. What we were just looking at coming out of the emulator. Where's our symbol file? Oh. Wrong file name. There we go. Yeah, so we can build this report. And here it is. And we had this formatting done at the end of the last stream. So we get a summary of all the functions that we were in over the run from when we turn on Profiler to turn it off. And then the number of instructions we spent in each one. Then we're going to break down by name and instruction count. So all these addresses are in this profile enable function. And so on for all the functions. Then finally we get a list of the symbols. So that's the address range that the symbol occupies in memory. Then the name of the symbol. Then finally, after all that, every record. And a record is an address that we sampled, the number of times that we were there, and then the name of the symbol, if we have it. So that's more or less where we left off last week. And the challenge that we identified while doing that was that the map file is generated by the Wacom linker doesn't show all our symbols. It shows some of them. You get these entries for your symbols. And this looks a lot like what's in our report, address and name. But some are missing because it only shows the symbols with external linkage in each object file. So what's that mean? Every function in our C files here, this is C language. Every function in here has a linkage type, and it can be external or internal. So these functions that are labeled static are internal linkage only. They are not visible to the compiler outside the unit. So here I'm in kernel profile.c. If I'm in another C file and I want to call a function, it has to have external linkage. So I can't call this flush function from another C file. I can only call flush from inside this file. So we call it down here. If we try to call it from outside this file, from another file, then the compiler will complain. Or the linker will, anyway. So then these functions without a specifier for linkage have external linkage, so profile init, profile step. Those are both visible outside of this translation unit, outside of this file. And that's because they're intended to be called from outside it. So profile init we call from the kernel main function when we're initializing the kernel, for example. And we have this whole linkage facility to be able to encapsulate functionality. In the C language, you only have generally one namespace, so we can't have another function somewhere else called profile in it. We can't have another function somewhere else called flush if it got external linkage. And we might want to hide this. So this is only usable from inside this file. We don't want to use it from outside the file. So by marking it static here, we keep it internal. Keep it from being exposed. Keep us from using it from outside the file. So it's a way to organize our code in more than one file and expose only what we want to be exposed. So back to the problem, those map files that the OpenWatcom linker creates gives us the addresses, the memory locations for only the symbols with external linkage. So in this profiler report, we ended up with all these gaps. And those gaps actually they didn't look like gaps, they looked like incorrect results. So there would be records that, for example, would say, I don't know, LFSR get. Or LFSR get, let's just say, for example. So it would say this, but it would actually be part of a function that was in between LFSR get and LFSR next. So it was misreporting. So that the task there was to get the symbols for the symbol names for the addresses for the symbols with internal linkage only, static linkage. And we couldn't do it from the map file. But by getting the symbol names, we'd be able to fill in these gaps. So the solution there was to stop using the map file and instead use the debugging information that the OpenWatcom linker can put into the executable file for us. That information is in a format called DWARF. And that DWARF's an acronym for something. What is it? It should tell us. That should be the first thing it tells us. But it doesn't. Wikipedia says up there. Unless it doesn't actually, unless it's not actually an acronym. Okay, the backronym, debugging with arbitrary record formats, has been proposed. Had no official meaning originally. Anyway, the linker will put this debugging information in, which would presumably include all the debug symbols for all symbols, despite linkage type. I have not really worked with DWARF before, so I had to read the spec and figure out how the information was stored in the files. So, as it turns out, OpenWatcom will just put the DWARF information at the end of our executable file. And there's not a great way to view this in just hexadecimal, but we'll just take a look. Now I made some changes, but originally when I added the option to the linker to add the DWARF format, it just put it at the end of the COM file. The COM file being the DOS executable file that the linker will create for us That's what our operating system uses with some modifications. So the debug information was just coming at the end of this. So actually yesterday, I figured out that the linker has an option to put the debug information in a different place. So here's our command to run the linker, OpenWatcom's linker. Debug dwarf is what puts the dwarf information in the file. Option sim file, that lets us put the information, the debug information, into a different file and not into the executable, which is kind of what we want here. We don't want it in our com file. It's going to make those a lot larger, and they're unnecessary at runtime. They're unnecessary when we need to start the program. We don't need them there, so I'd rather have them as a separate file and process them that way. So with this option sim file, we create a different file. At the same time, we create the executable file. And we just do a WSYM extension there. So if we look at that, that's this whole business. So this is the dwarf debug information. And this is the one for the kernel. So it's about what? 16 kilobytes? So I had to figure out what this file format is and how it works. If you look at the beginning here, where it says ELF, ELF's another object format, executable and linkable format, ELF. And that's another format. And as it turns out, the dwarf information gets placed inside of an ELF file. So we had to go and figure out the file format details for ELF and dwarf to make progress here. So in object files, and this essentially tells us what's in ELF. There's a header. Most file formats have one, not all, but many do. There's a sections section. So it's a place where basically kind of like a table of contents for the file. And string and symbol table contains abbreviations and such. And relocation we don't even care about. So the dwarf spec, and this is dwarf 2.0, and that's what OpenWatcom uses. The latest version is 5.0. It's a bit different. The dwarf spec says that we create a section called debug info and then do stuff in there. There's a section in the ELF file called debug info, and that specifies the debug information for the dwarf. There's not, in dwarf, there's not a really good overview, I don't think. There may be a diagram we can take a look at here. Where is the table of contents? No. If I don't see it, I'm just going to skip on. I found it a little hard to read because I felt like it went from the details to the general a little bit. Anyway, this is sort of how things are arranged. Yeah, we've got a debug info section, an abbreviation table, where we define different debug data structures. And then debug info, we have some entries that refer to these kinds of structures. But at the end of this exercise, what we came up with was a program that lets us read this stuff. So we've got all this. This is our input. And I made this DWARF utility that will show us what's in there. Yeah, so here it is. A debug abbreviation. This basically sets up a record structure for what we're going to put in there. It specifies the names of the different fields that are going to be specified. And then each of these debugging information entries, DIEs, fills those fields in. So a quick example here. So here's the code for code number 2 in the table. And that has one attribute, and that's a string. So here is our entry. Code number 2, that means it's going to have one name, one attribute called name, and it's a string. That's the name of our file. Here's attribute 4, or abbreviation 4, code number 4. So we're going to have an address for the program counter, segment, which is going to be another address, a name, and if it's external or not. So here we go, code 4, an entry. And then here those things actually are. So program counter, it's external, yes or no. The segment, code segment, and then the name. And there's a lot of those. But that's exactly what we want. That's what we're looking for. Each of these things has a name, code segment, instruction pointer. And that's exactly what we need for the profiler. So looking back at the report, pretty similar. Whoops. Here's our name. Here's the segment. Here's the instruction pointer. So we're just transforming that data. So lots of work, but well worth it to be able to use the profiler. So I have a test. Test profile. We've got a few test cases. I'm not running them all at once right now. I'll explain why in a minute. But these basically go from simple to advanced. So test loop. We turn on the profile and turn it off. We do this at the beginning and end of every test. Turn on profiler, generate some random numbers, then turn it off. That's all. So that exercises inter-segment code only, just local code. It doesn't make any system calls. And that's just to work the, happiest case. Most likely succeed case. Because it's once we start making system calls, crossing the boundaries of segments, that we're more likely to start having problems with profiling. Then our next case is to make some simple system calls. So again, in a loop, we first do an op, no op syscall. All it does is call the kernel, and the kernel says, okay, you called me, and returns. And then one that's almost as equally simple. All it does is get the time. Then the final test case is to turn on the profiler, fork the process, replace it with another image, with a hello world image. Basically create a new process and run a program. Do that, then have the test process wait till that child process is exited, then exit itself. That's the kind of the worst case. So anything that is intrusive between the user space and kernel boundary is much more likely to cause any number of problems than anything that stays in intersegment code, doesn't call the kernel, etc. And the fork and execute does the most of that kind of stuff. So simple to advanced. And I've been running them and they look pretty good right now. There are several things that we could work on, several things that we could do next. One thing I would like to do is get some information when we turn the profiler on and turn it off. So right now, if we were to run all these tests in a row, we would just get this big long string of data over the serial port. We'd have no way to separate it out. The profile doesn't send any sort of information indicating that it started or stopped. So all the results would just be together. And I do want to add that. It just is a little more work than it sounds like, I guess, because to actually get that on and off signal to transfer that state when we start the trap and single step interrupt, we have to call the kernel for that. And that's normally done with either a system call or by writing to a special file. In this case, it'll be writing to a special file. I will add a new system call for that. So we can do that, that's one thing. There's some other stuff that I want to get to pretty soon. These make files are pretty complicated, or messy, I guess. We mostly just link object files together as needed. I've started to try to organize things into libraries. Should have done that earlier. When I first started with the Open Wacom, I wasn't familiar with the utilities, wasn't sure how that sort of thing was done. So I just built a system on linking object files together as needed, and that worked okay, I guess, for a long time, but it does make for some messy make files and just fidgeting around and moving file names around in these files a good bit. It causes other problems too. It can be hard to see dependencies. It makes it harder to view the system without making diagrams for it and stuff, so I would appreciate some more encapsulation of things into libraries. So that's something we'll get to pretty soon. I also want to act on alt a little bit. Start looking at how the profiler results, what they mean. Looking at the worst offenders, I guess, and the slowest code. And seeing what we can do. Now this test case here, this is running QEMU, and this runs fast here. But in some of the other emulators I have, the XT emulators, oh, this runs very slowly, and that's the reason for profiling in the first place, because we want to make things run fast on those targets. Those are the minimum systems we're targeting. So there's some problems on the systems too. The profiler doesn't seem to be working. Let's actually try it. Is this working right now? No, let's see if we can fix this real quick. This is what I was working on before stream. Still no dice, why not? I'm having to build virtual XT from source right now. I think I see. There we go. Good. That should work. I'm Metal Machine. What's TSA? Oh, I got it. I had to zoom out to understand. Seems to be working. Hope your evening's going well, Metal Machine. Okay, so I just mentioned I'm having to build Virtual XT from source right now. And I mentioned a week or two ago that I found a bug while starting to develop the profiler. where virtual XT will not... how is it? I forgot now. Okay, yeah, if the trap flag is enabled on the 8088 CPU, virtual XT will never generate timer interrupts. And we kind of rely on timer interrupts for everything, really. With task switching. So it took me a while to find that, but I reported that upstream, and Andreas, the developer for VXT, actually confirmed that that was indeed a bug there. So I have a fix, but I have to build from source right now to apply that fix. So now we can run this guy. All pros in this case, in my opinion. This option's been removed, serial debugger, and it's now been moved to a Lua module. Oh, I hate it when that, well, I do hate it when that happens. If they're not going to end right at the same time. But I guess I'd rather run out of salsa first. Because I can still eat the chips in this salsa. But not the chips. I got nothing to do with the salsa, unless I have a burrito. You always run out of one first, I guess, no matter what. Unless you intentionally adjust your ratio while you're eating and make sure you end at the same time. Hi, Tibur. The one and only. Oh, I forgot to pop out the chat window. What is this? Got it. Salsa is so good. And chips. Food in general. I do like food. I'm momentarily distracted by thinking about food, but I'm thinking about what to do next here. Okay, I think I remembered. Salsa is so good though. It's like the best application of tomatoes, I think. Tomatoes, being pretty naturally good. They have a nice flavor to them. And salsa just improves on that. And get that cilantro in there. Oh, the OS. Okay, this is a retro operating system. It's a 16-bit real mode operating system, meaning it will run on x86 CPUs, like the one in most PCs. Most Macs, actually. Also, all the way back to the first of that line, or close to it anyway. This guy. The IBM 5160 XT. And that's it. So it's a retro operating system, and the goal of that, besides, is to learn how to make an operating system and get better at programming. Those are my selfish goals around it. But the goal for it is to give people a currently developed OS that they can run on their computers of this vintage. Because there aren't too many options there that I know of. Well, you would install it on your actual PCXT machine. Put it on a floppy disk. Put a floppy disk in the drive. Boot it up. So let's see, I might be able to do a demo real quick. I have not checked recently to see if the demo works. Tests are running. The good old days. We have a console. Yeah, so you would, right now everything fits on a floppy disk. A 760K floppy disk. So if you had one of those 320K floppy drives, then I would not be able to give you a disk right now. I have plans for that, I just had to split it on more than one disk. But you can put it on a 720K disk and you could boot up your XT and this console would come up. I haven't done it in a while. The most vintage computer that I have is a Pentium 100. And quite a while ago, with a very early version before I added processes and multitasking and everything, I did put it on a disk and put it over on that machine and it worked. I need to do that pretty soon. Once some things are worked out and fixed. So this console runs, you can type ls, I think. Why is it not working? Like I said, I have not checked if this demo works in quite a while. Wait. Yeah, so do I. And I'm actually pretty sensitive to that. Like I get distracted and upset when I can't do things without ads. I have to be able to get them out of my way. Okay, so this kind of works. So you can type ls, you can get your list of files. That's everything on the floppy disk. You can run a program. You can look at the contents of a file. Other stuff. There's a few other things too. There's some stuff that's not working, so I won't show anymore. Console switching. You can have two consoles open at the same time and switch back and forth from them in different processes, which is unusual for an operating system for that type of computer. DOS didn't have that. Though I heard the other day there was a multitasking DOS. I don't think it got much widespread use or adoption. Maybe a special case, special made for a single vendor or something like that, I'm not sure. So I was going to run this on virtual XT. But, okay, yeah, so a command line option was removed, changed to a Lua module. So I need to make sure that that still works. Oh, and I need to reconfigure. Times are tough for Popeyes. Yeah, well, I was talking to somebody else about similar, like not exactly the same thing, but the same sort of concept. Is that food is a thing you do every day. So if something changes around that, you're going to notice. If you can't get what you want or whatever, then it's like a potential sort of change or disruption in your life on a daily basis. And I feel you. I go to the grocery store, they don't have what I wanted. That's disappointing. We got some tests running on Virtual XT. Okay, it's finding a config path. It does not see our modules, probably because it's a relative path. I'm sure that would give you some perspective for sure. Did you go fishing? There we go. There's our log output. Okay. Now we're running some tests. I'm going to run these. I was able to hang the system with the profiler turned on pretty easily before. I just want to try it with the new test. Something I always try to appreciate, is that there are so many different ways to live. Travel does help give that perspective sometimes. Let's try this and see what happens. It might be rung, it might be hung. We actually use COM2 to output the serial data. Let's see if we can get that running on Virtual XT. We might be able to. Not the file we wanted. Got to be at least one, I guess. Someone called me the Bob Ross of gaming once, but I'm sure I've not been the first to get that. Maybe I can be the first for OS development. So COM1 is at address 3F8. COM2 is at 2F8. So let's see, I won't mess around with this too much. But I'll mess around with that a little bit. In QEMU, you can enter command line arguments to add serial ports, which is nice, very handy. So the reason we have two is just so I can send the profile data separately over one, because that's all binary data. That's just a list of code segment, instruction pointer, count values. It's 6 bytes per entry. So until I figure out a way to interleave it with text logs over the serial port, it's easier just to have two serial ports. We can do that. We can have a log reader that sorts out the binary stuff from the text stuff. Once I do what I'm talking about here, which like add a couple of header and trailer bytes to the beginning and end of the profile data, then we know when it started and when it's ended. Until I do that, this is the easy thing. So let's see if this works. Of course, it won't be sorted out into separate files, even if it works, but I want to see. Yeah, some PE teacher's gonna be like that for certain. I don't even remember mine. I guess I only had it freshman year. So where's our output? one of those, huh? Seems like we're locked up, so I'm going to try it without the profiler on. That works fine. Yeah, so we're locking up somewhere. I'm not going to troubleshoot it with Virtual XT right now. Unless I decide to, I don't know. I kind of want to. I want to just dig in. But no, there's too much. Too much to dig into. So I won't, and we'll come back to that. Yeah, this is so long ago. I don't think my PE teacher cared. I think basically the only requirement for that class is that we put the gym clothes on. So it confirmed Virtual XT doesn't work right now. That's something I have to look into. The bug is fixed, but we've got some other problem there. And we can't get the output anyway because of the aforementioned serial port issue. So let's look into starting and stopping this. Right now, we've got these functions. Well, it's just one. It takes a Boolean input. Enable element, so we turn it on and off. You call this from user space. All it does is set the trap flag. When the trap flag's on, then the single step interrupt gets generated before every CPU instruction. Every, in quotation marks, it's not actually every, but generally. So when that single step interrupt gets generated, this is our interrupt handler. We save the CPU state. We put the current value of the code segment and instruction pointer into registers and then call the profiler. And the profiler sends it to the serial port. I want to be able to send start and stop commands because we need to be able to separate stuff out. So if I'm looking back at this, we've got 3 tests. I'm going to profile them all individually. So I want to start and stop the profiler before each one, get different results. Right now, if we start and stop it, it doesn't matter. Like once the results come back, they're all just going to be all mixed up together. I have no way to separate it because I don't know when one starts and one stops. So we need to record the start and stop event. Right now we got no means of doing that because we turn the trap flag on, this stuff starts happening. But there's no way to know when we get into this interrupt if the trap flag was already on or if it was just turned on. At least not any way that I can think of. There could be something I'm missing, but as far as I can tell, we got it to track that in some way. So we need to, in the profiler, we have a context, so we can add something here, Boolean, called like enabled. Then we turn it on. If it's not already enabled, then we send this start message. If we turn it off, if it is enabled, we send this stop message. This is kernel code though. User code can't call it directly. So to get that initial enable message to the kernel, we're gonna have to send it through the file system. Alternative would be to use a system call, but I'm not going to add a system call for it. That's what device files are for. So we have this concept of device files. Linux has it too. So do other Unixes, I guess. Part of the whole everything is a file kind of approach. Linux has a directory called dev. Devices are under that. And you can read and write from and to device files. So we got the same concept. The only one right now we have is pid. Dev pid. Process ID. We've got some under proc. So we'll probably add a new one called dev profile. And when we write to that, we'll turn on the profile or turn it off. I don't know about the organization of this code. Right now, this is under process.c. I don't know if device files like this really belong there. We may have to switch this out. Pull some of this code out into a different unit. But I'll think about it. For now, we'll add it here. So here's what we're going to do basically. We're going to say, let's start some scratch buffers. There's going to be a file that we can write to. It'll be called dev profile. When we write start to dev profile, turn profiler on. Right stop to dead profile. Turn profiler off. That'll be our approach, and when we write to the file, that's going to make a system call. Then that code where we just were will, at that point, call profile enable function in the kernel, which can do this kind of setup stuff that we're talking about doing. Startup and shutdown. So let's try it. I'm going to take a break for just a couple of minutes here, and I'll be back and we'll do that. First thing we'll do is modify our system profiler code to actually try this. Yeah, or at least open data. I haven't used these APIs in a while. Kind of forget how they work. Yeah, maybe so. If you don't have the data locally in the first place. And we're all just searching one copy. Alright, the old function is behind conditional compilation. Here's what we're going to do now. So we're going to open /dev/profile for writing. Write a start message to it. Actually, that's conditional, so and we need the size. That looks like what we want. So we'll try it. We should get an error. I'm not sure we will. Okay. So we didn't get an error. We got an assertion. An assertion means that we put a set of assumptions in the code that we want to know if they are not valid. So when we call write, MIO write, write to the stream. The only one that supports that right now is the control file for processes to start and stop them. We're trying in a different file. And so it says you can't do that. So there's a couple things we got to do here. We've got a top level device file. We need a match on the first / past dev and match the word profile past that. I'm not sure if I like the error handling here, but I'll come back to that. Okay. You here to be a programming kitty? Okay, so at this point we managed dev. This is an iterator, a string iterator. So when we have a string that needs to be broken into parts using some separator, like a / in this case, we can get an iterator object over it. It makes handling that a little bit easier. So we match dev. We get the next element in the iterator. There's one we need to handle, PID. That's an existing one. Let me add a new one called profile. It still does for me. And any more than one level of pointer in direction. Gets confusing to me pretty fast. I try to get out my paper. One bad habit that I developed a long time ago is when something's not working, just mess around with it until it starts to work, and that sometimes works, sometimes it doesn't, sometimes it seems to work, but then you just got your special case working by coincidence. I'm always better off, I find, breaking out a notepad, sketching out the data structures, actually understanding what's going on. But old habits die hard. Yeah. I've seen a lot of code, I've written a lot of code that seems to work but doesn't really. It works for a narrow case. Around it. Stops working. Working in this environment definitely started to drive that lesson home better, though, I would say. Probably anywhere where the stakes become really high from memory errors, concurrency errors. Both of those things together. In a single threaded environment, there's only so much can go wrong, and it's fairly easy to narrow things down, but outside of that, terrible things can happen if things aren't correct. Finding something can take days. But all those easy single-threaded problems add up too. It just doesn't seem bad in the moment. Because you find the bug, you fix the bug, but you still have to find it and fix it. What if you didn't have to? When the bug is elusive and takes 2 days to find, it's the same lesson, but it hurts a little harder. It stings more. I try to think of ways to get better. I'm still not nearly as good as I want to be. I've heard people do things like keep track of all the bugs they created per week, which I've done a couple of days at a time, never a week. Because there's a lot of overhead in that kind of activity. It's like, what constitutes a bug? If my function didn't work the first time, is that a bug? Probably not. But maybe I should track that. You know, you just get on this rabbit hole and you start self-evaluating in any kind of way. Okay, this is our error case. So if we try to open /dev without anything else, we're just going to assert for now. That should return an error. Dev PID should preserve our existing behavior. Dev profile opens profile. So we have a category that's attached to this file. This is the kernel's concept of a file, an open file, and we have this enumerator that classifies all the types. So I added one. Again, I'm not sure these device files belong in the process file system. I think we're going to have to pull this out as part of this work. But that looks good. So file category is going to be dev profile, and then when we up here, now we need to handle this category. Need to have requirements before you can call things bugs? I don't know. If you have a function that takes some inputs and returns some outputs, and it doesn't return the expected outputs to the expected inputs, that's a bug, right? So yeah, I guess maybe you need a requirement before you can write a function. I'm just looking at this, I'm not sure what this does. I think we... Alright, Metal Machine. Good chatting. Talk to you later. Have a good rest. Index we don't care about. Index is not even used, apparently. Okay, yes it is. It was expected to be used, but not. We don't actually use it in this function. Anyway, here we're going to turn on the profiler. So just like the system interface of the profile, we're going to have this function, profile enable. So let's just make sure it's working. So do this based on the value of the message. So let's just take a look at this again. Here's the new user profile code. So we open this file, then we write this message, start and stop. This MIO write, this eventually ends up calling this through the kernel. So data is going to be what we pass in here, the message. Start or stop. So data should be the string, and then it should be the size of the string. We can compare the string. So hopefully this makes sense. I'm getting warnings. I don't know if they matter or not. Okay. Data type warnings. Oh, we can't declare this inside the switch statement. So we take the message here. If it's a profile file, take a look at the message. If it was start, we enable. If it's stop, we disable. Otherwise, we assert. We need to eventually return an error here. But I'll come to that in a bit. Oh. Now include the header for the profiler here. Okay, let's try it. So when we do this, we should just get these log messages. Enable true, enable false. We ended up in a loop, it looks like. Which I'm not sure why we'd end up in a loop. Let's see if we can figure it out. We might be failing at the VFS layer before it even gets here. That looks okay. Let's just log the value. See what's coming in here. So we're kind of coming in, file PID. Then file profile comes in. We get not found. Why? Probably this logic down here. Oh yeah, and this assumes that incorrectly that dev means PID, dev PID. This logic looks more complex than I think it probably needs to be. I'd like to make this better, but I'll need to think about it. But again, this device stuff maybe shouldn't be in the process stuff. And that may be the real issue here. But anyway, when we add our new category to the category of exceptions where it doesn't try to look up a PID. I think that's going to make our immediate error go away. Good. So now we open it. And it does open, and we hit our assertion here, so our message isn't what we expect. I haven't used these I/O APIs in a while, so I need to make sure I'm actually doing this right. Also, do we even have tests for I/O write? Okay, looks like we use them, fairly well established. Yeah, size of doesn't work. I'm brain farting. Why doesn't that work? That should be giving us the size of the string, right? Oh, it's giving us the size of the pointer. Right. So can we do this at compile time? No, because the pointer points the character. So will the compiler let us declare as an array? Yeah, okay. The size of a pointer is the size of the pointer. So if we declare the strings as arrays instead, then the size of gives us the size of the array, and then when we name the array, we get a pointer to the first element of the array, so we don't have to change anything. Enable true, enable false. There we go. So now we can do what we really want to do, which is to do a kind of initialization when we're in the profiler. So we're going to make a special record. Here. So we'll use the same record format. So we're just to recap, what we're doing now is when we enable the profile, we're sending a special record that tells whoever consumes this data that we're starting. This is the beginning of a session. So we're going to do that by setting code segment to 0. We'll just send out, we'll make the whole record 0. And when we turn it off, set code segment to 1. I think that shouldn't conflict with the record format because there should never be any code there. A code segment 0 or 1. I believe that's all going to be in the interrupt vector table of the BIOS. So you'd never get a false reading that way. You'd never have actual code come and confuse whoever's reading the data and have them think that it meant turn the profiler on or off. At least I think we're okay there. So, and we'll write the record. New record is, that's a structure, so we need to take the address. We also need to set the trap. So we'll move that into this code. That might do it. Let's see. As soon as I change the music for us. Different one. No vocals. It's not a stupid question. Thank you for asking it. Also, welcome. Leonard Euler, 23. Is that how you pronounce that? If not, let me know. The profiler creates a profile of CPU execution. And the reason we're doing this is because I'm at the point now where a lot of features are working. Some of them aren't working very quickly, particularly on hardware that's older. This operating system targets, at a minimum, this computer, the PCXT, with an 8088 CPU. Very slow by modern standards. And some things are running pretty slowly on that. So in order to speed things up, we need to know what's running slowly and what's not. And the profiler is one part of figuring out how that works. There's different kinds of profiling. This one is a tracing profiler. And what that essentially means is when we've turned the profiler on, then before each CPU instruction that runs, we record the instruction pointer of the CPU, the address that the instruction sits at, where it's about to execute. And through doing that, we can see where the CPU spends more of its time. Because, say in loops, where something may be running 1,000 times, you would have a higher count for those instructions. If we go here, this is a report from the profiler. Actually, let me see if this actually works, and if it does, then it's a better way to start the demonstration. Okay, it looks like it worked. So if you saw this window on the right here, labeled log2, this just has a bunch of entries of 3 numbers. The first number is the code segment. The second number sorry, the first number is the instruction pointer. The second number is the code segment, and the third number is the count. So that's all being sent over the serial port of a computer. And in this case, we're into a log file. That log file is processed and aggregated with the debug symbols, and from that we create this report. So this shows us the functions, the C and assembly language functions, and the number of instructions that we're executing in each of those functions. That's built by correlating the list of debug symbols, this business, against all the counts from the profiler itself. That's the profiler. And then from that we can say, okay, if this thing that we're profiling is being slow, then we need to look into this LFSR next function because that's got the most instructions happening there. And then just go down the list and kind of figure out where optimization opportunities would be. Maybe profile smaller sections of the code. This is a virtual machine, and it's not in this case, it's not even a virtual machine that emulates that, the PCXT. This is QEMU. And that's where I do most of my development in QEMU and Box, which are both pretty fast. I have two emulators that target that XT class machine. One is called Virtual XT and the other is called Marty PC, so I can use those to get even closer to that. I don't personally have an XT myself. The slowest thing I have is a Pentium 100. I'd like to at some point get an XT. But what I have right now works pretty well. It will and should work on hardware. I have a USB floppy disk drive. And I haven't done this recently, but I've put the operating system on floppy disk and booted it on the Pentium and verified it to work there as well. But yeah, so to improve the performance, especially on the lower end hardware, is the whole reason behind developing the profiler. I started out with doing logging statements, so just write logs in different parts of the program and then see, like, in between two sets of logs, how much time is it taking? If it's taking a really long time, then investigate that section of code. But that's kind of time consuming and kind of error prone too in my experience. So hoping the profiler will make that activity faster. Although it itself takes a lot of time to develop. If you have any other questions, feel free to ask. I mean to mention this, and I always say at the beginning of a stream, but I forget to say it throughout the stream. But if anyone has any questions, just feel free at any time to ask them, and I'll stop or maybe finish what I'm talking about and answer the question. No need to wait. So this looks like it works, because now at the beginning of the log file we get this all zeros. So that's an indicator that the profiler started. And then at the end we get the the second word is 1, and that indicates that that's stopped. So that'll help us segment out our logs. So we can test this. I can uncomment these last two and run it again. That was fast. Did it actually work? I guess it did. Yeah, we got 3 starts and 3 stops, so it's working. So this is good. So the next thing we have to do is go into our profiler report generator and handle those start and stops. Which I don't think I'll do that right now. I'll probably do that tomorrow. First thing. So this is pretty good. I'm pretty happy with this progress right now. It would be nice if everything were running on Virtual XT. So I may look into that tomorrow if I can get all this tested, up to quality, committed. That's what the path forward looks like. Get it working well on Marty PC, on Virtual XT. And then actually measure what's causing problems. Fork and execute are pretty slow on VXT right now. So we want to dig into that, improve that. So this has taken a while to get right. And we're still not through, since it's not working on all the emulators, the XT class stuff. But I think it'll be worth it. And we had to go down this side quest of parsing the ELF and DWARF debug information to be able to get symbols with internal linkage only. But that's something that I have wanted to have anyway. There's been times I've wanted to trace CPU execution into static functions and haven't been able to get that with the OpenWatcom map files. So this will help us in a couple of different ways. And I may find other uses for the debug symbols that I'm not thinking about right now. We have no functioning debugger at the moment. I did start on one quite a while ago and haven't worked on it in a while because it was difficult to implement, difficult to get it to work with multitasking and everything else. So, but we may have to write one at some point. Why not use GDB? We can't use GDB because GDB is not compatible with 16-bit real mode CPUs. If the OS were targeting 386s and higher, we might be able to do that. But because of the decision to support 8088 and 286 in real mode, we end up having to create a lot of these tools. The available alternatives won't work on these targets. Some things could be ported, conceivably. A lot of modern stuff is going to require more memory. I'm going to assume that more memory is available than we have here. This operating system right now puts every process into its own 64K segment of memory, including the kernel. So that's all you get, unless you break out of it with assembly language code. But then you step on the assumptions of the kernel. That limitation could always be removed. We could handle larger blocks of memory at some point. Not in scope right now, though. It would be nice. There's definitely, I mean, I think about it pretty frequently that it would have been smarter to start with a 386 target to be able to take advantage of memory protection from the CPU and software that runs only in protected mode. But I don't know. Not having done that before, I don't know what all the challenges are around that, so. Well, it sounds like that might have been easier. I could have hit a ton of other problems with that. I would like to, at some point, target the 386 as well. Most of the code is in C. That doesn't necessarily mean it's portable, but a lot of it should be. The bulk of the assembly language code is in this file to handle interrupt handling, and is very 8088 specific. But there is other assembly, and there's inline assembly in some of the C files also. So not super easy to port to another target. But the main challenge is just doing the work, and also just understanding everything, all the nuances of the 386 in protected mode. But it would be nice to have a target with memory protection at some point. Another possibility is the 68,000, the Amiga's CPU. And I've thought about just doing that a number of times, but each time so far I've deemed that a distraction. I thought it'd be better to stay the course on this, at least for a while longer, at least until we're complete with what I think is a minimal subset of features, release this, and then go from there. So I'll be back with another one of these programming streams probably next week. In the meantime, I'll be uploading this one to YouTube. And my YouTube channel has a few others. Past streams. This topic interests you? Actually, let me just put a link out there. If anyone has any questions, feel free to ask. I'm going to see if someone's in the software and game development category that we can raid. Yeah, that works pretty poorly. And GDB has to support your remote. That's kind of supported in QEMU, but not very well. It also still assumes that you're in protected mode, so it shows the instructions. Again, this is from memory because I haven't tried this in a while. But I went down the path and was disappointed. The GDB still assumes that you're in protected mode as far as I remember. It just shows the instructions as if they're 16-bit. So it doesn't really have any knowledge of the memory segments and stuff. And it just didn't really work. It doesn't do the segment offset calculations correctly. The box debugger is pretty good. It works pretty nicely, and it's gotten us pretty far. Downsides are it only works on box. And it's not terribly well integrated. You can use debug symbols with a symbol file that you can generate. It could be better, but it's still fairly good. And all these things only work in their respective emulators. Box debugger or remote GDB. Ideally, you have a debugger that runs on the host. Yeah, it is useful for basic debugging in the bootloader. It can be useful there. Past that though, I found anything else to be better, like the box debuggers. And you're still running it on the host and remote to the target, right? Not running it in the target itself. So if you're on hardware, you're not going to be able to debug that way. It's a better option than nothing, though. If you were developing a kernel in protected mode and you can support that file format, then you run GDB inside your kernel, no problem. Inside your emulator or hardware or wherever else, because it'll be able to actually port it. Or not even port it, but just compile it. Hi, wire red. Is that right? I'm not familiar with that. Just looking at the image, it looks pretty good. And as someone that almost uses open source and free software exclusively, I would definitely try all those alternatives first before I go to anything proprietary. So yeah, it looks like a good option. I'd say give it a shot. IDA is the one that always comes up for reverse engineering. And I've not used it personally, but I've seen it used in presentations by reverse engineers who do things. It seems very powerful. It's also a few $100s, I think, at least for a pro license, so you can get what you pay for. How are you approaching that, Wire Red? Do you have some materials to learn from? Tutorials? Cheat engine is one that's come up a couple of times for reverse engineering. CIA software? What does that mean? That's one that's come a few times, cheat engine. Oh, I see. Gidra's the name of the software. Yeah, well, that sounds like a pretty good approach to me, Wired. Start smaller and build on it. It's not a field I pursued too much, reverse engineering. I started doing NES ROM disassembly a few months ago. I've done some reverse engineering in the past. Not something I spend a ton of time doing, but I could dabble, I guess. Yeah, that's awesome. Yeah, that's how all these things go. Small victories, and then they start adding up, right? That's how it feels for me anyway. Small victories add up to larger victories. But the X64 DBG looks pretty good at a glance. I try to pick things that will work across OSs, if possible, and things that I think will be around in several years. Hopefully won't go away. So Leonard, if you're still there, you followed along with the Udemy course. Are you pursuing OS development? Is that something you're working on? I'm looking for someone to raid. I mostly do gaming on Twitch and mostly know people from gaming on Twitch. Not software development, so I'm gonna have to find some friends for this. Okay, I think I found somebody. Oh, like 64 DBG. So that's an endorsement for that? Huh. Nice. I don't use Windows, otherwise I would check that out. Oh, I see, Leonard. Yeah, work has a way of doing that, huh? Contributing feels nice, though. I don't contribute as much as I want to. But I try to sometimes. I recently contributed code to the FCE UX, the NES emulator, and also the Virtual XD emulator that I've been talking about a little bit that I use with this project. It's nice. Okay, I think I know where we're going. Thanks everyone for coming in, hanging out, saying hi. Nice to see some new people coming in and chatting on this topic. I'll probably be back. I sometimes try to do these twice a week, but I rarely get to be able to do it. But I will almost certainly be back next Tuesday, if not before, to do more. We might be doing more profiler stuff, might have moved on to something else by then, I'm not sure yet. But we'll see. So if you're into this type of thing, keep me in mind. I'll be around. And I will be back Wednesday, Friday, and probably Sunday for my normal content. I usually do retro gaming. Absolute Aaron, welcome in. Alright, we're going to go hang out with Soulburn. Where did I learn to do it? I tried. My first attempt was probably 2014. And I started by just following the tutorials on the osdev.org site. I did not get very far. That's not to say the tutorials are bad, I just wasn't ready. And since then, I did a few other things. I got more familiar with CPUs generally. I created partial emulators, several of them. Game Boy, NES, one or two more. So I got more familiar with assembly language and CPU architecture. And I built a couple of computers. Worked on building a CPU with discrete logic, which I didn't finish. Most of my projects are unfinished. And then I built a computer around the 6502. I'm looking to see if I have a page on that. Probably not. So just slowly built up to it. And then I started this operating system last year. Just a little more than a year ago, I guess. Right around a year ago is when I started working on it pretty seriously. And all that background over the past few years helped a lot. So where I was lacking this fundamentals when I tried it out the first time, it was at least manageable. Certainly not easy, and I've made a ton of mistakes, and there's a lot to do before actually releasing this. A lot of mistakes to undo. But working on making those tools, disassemblers, debuggers, emulators, building computers on circuit boards if you can. Doing all that kind of stuff. Fundamental stuff, and particularly on like older, slower, simpler hardware. That'll help out a lot. Learning digital logic. I'm around. Feel free to hit me up on Twitch or on Discord. Always free and enthusiastic about helping out anyone any way I can. Here's a schematic for a basic 6502 CPU. Learned a lot building something similar to that. All right, we're going to hit up Soul Burn. Thanks, everyone. Good chatting, good talking to you. Thank you for your interest. I'm not going anywhere. I'll be back next week. Raid Soul Burn. I'll be back tomorrow with Castlevania 3, but I'll be back next week with operating systems. And I will see you all later. Have a good one.